Welcome to this video tutorial about measurement uncertainty in the AQC document of DG SANTE. This first part of the tutorial is focused on the proposal introduced in the last revision of the document in its Appendix C on the estimation of measurement uncertainty of results based on intra-laboratory validation and quality control data. This tutorial has been prepared by Professor Antonio Valverde and myself, Carmen Ferrer, from the University of Almería on behalf of the European Reference Laboratory for Pesticide Residues in Fruits and Vegetables. Before starting, it's convenient to highlight two important premises which will be very useful to understand the AQC guidelines on measurement uncertainty. First, it must be taken into account that the nature of the test methods used in pesticide residue analysis precludes a rigorous and statistically valid calculation of measurement uncertainty. This premise is supported by the ISO 17025 accreditation standard. And second, as stated in the EURL-FV guide on measurement uncertainty in analytical tests, in multi-residue analysis of pesticides, it is not the goal to obtain very accurate measurement uncertainty estimates for one specific pesticide in a particular matrix. It's more important to obtain an overall and realistic estimate for a wide variety of materials and analyte levels covered by the validated scope. The latest revision of the AQC guidelines is document SANTE 12682 of 2019, and a detailed analysis of this document leads us to conclude that the term uncertainty only appears in Appendix C, where some examples for estimating the uncertainty of the results are included, and in Section E, reporting results. Although in Section B, sampling, transport, traceability and storage of samples, the word uncertainty also appears, it's only to specify that the contribution of the sampling variability to the measurement uncertainty of residue analytical results is not treated in this document. In Section E, reporting results, the term uncertainty appears for the first time in paragraph E4 within the subsection entitled Correction for Recovery. It also appears in paragraphs E7 to E11, which make up the subsection Qualifying Results with Measurement Uncertainty, and finally, it also appears in the subsection entitled Interpretation of Results for Enforcement Purposes in paragraphs E12 to E15. In these paragraphs, the decision rule to decide when a result is non-compliant with the MRL is established. All the guidelines related to measurement uncertainty in Section E, reporting results, will be presented and discussed in the second part of this tutorial. This first part of the tutorial is dedicated exclusively to describing and evaluating the examples included in the last revision of the document in its Appendix C, Proposal 1, on the estimation of measurement uncertainty of results based on intra-laboratory validation and quality control data. Appendix C in document SANTE contains a series of examples for estimation of measurement uncertainty of results in a laboratory based on the Codex Alimentarius guidelines. Only the uncertainty components associated with the intra-laboratory precision and the bias of the test method are taken into account, and both uncertainty components are calculated from intra-laboratory validation and quality control data, or from the results obtained by the laboratory in different proficiency tests. Therefore, these estimates do not include the uncertainty component associated with the process of preparing the test sample from the sample entering the laboratory. Two different ways of carrying out the uncertainty estimation are described in Appendix C. In Proposal 2, the estimation of a generic uncertainty value for multi-residue methods is proposed based on a combination of both the global intra-laboratory precision and the uncertainty associated with the global bias, estimated from proficiency test results. The calculus in this Proposal 2 use validation, quality control and PT results obtained from different pesticides and different matrices of the same group. In the case of Proposal 1, the uncertainty is estimated for each pesticide using only intra-laboratory validation or quality control data obtained on different matrices from the same commodity group. This is the proposal that we will describe and analyze in this presentation. Appendix C of the AQC document is based on the measurement uncertainty guidelines published by EURochem, Nortest, EURL-FV, and especially by Codex Alimentarius, since the Codex Guide 59 of 2006, which with its amendment of 2011, is the only one of these guides that is specific for pesticide residue analysis. Specifically, Proposal 1 in Appendix C is based on the following 4 consensual conclusions on the use of intra-laboratory validation and quality control data for estimation of measurement uncertainty. The first conclusion, already mentioned, is that to estimate the relative standard uncertainty for a given pesticide, we need to know both the relative standard uncertainty associated with the precision and the relative standard uncertainty associated with the bias. The second one is that in pesticide residue analysis, both the precision uncertainty component and the bias uncertainty component are estimated by using the recovery data obtained from the same recovery tests. The third, and perhaps the most important conclusion, is that the component of the uncertainty associated with the bias must always be calculated, even when the bias is 0. This uncertainty component is calculated as the combination of both the root mean square of the relative bias obtained in the recovery tests and the relative standard uncertainty of the spiking level. However, when the recovery test samples are prepared by using certified standards and they are properly calibrated and verified using verified balances and volumetric material, it can be assumed that the uncertainty associated with the spiking level is negligible. Based on these conclusions, Proposal 1 in Appendix C proposes an estimation of the relative standard uncertainty for each pesticide by using the recovery values obtained in N recovery tests carried out on different matrices of the same commodity group. When the analytical results are reported and corrected with the recovery factor, the bias uncertainty component is calculated as the root mean square of the relative bias values obtained in the recovery tests. When the analytical results are reported corrected with the recovery factor, that is, multiplied by 100 and divided by the mean recovery, the bias uncertainty component is actually the uncertainty of the value of the mean recovery, which is equal to the relative standard deviation of the recovery values divided by the squared root of the number of recovery tests performed. In both cases, it is assumed that the uncertainty of the spiking level in the fortified samples is negligible. On the other hand, in all cases, the precision uncertainty component is assumed to be equal to the relative standard deviation of the recovery values obtained in the N recovery tests. Let's now look at the final formula that we should use to calculate the relative standard uncertainty when results are reported and corrected with a recovery factor, so there is no recovery correction. From the results of the N recovery tests, both the mean recovery and the relative standard deviation of the recovery values can be calculated. As already mentioned, the precision uncertainty component will be the relative standard deviation of the recovery values. On the other hand, the relative bias obtained in each recovery test is calculated by subtracting 100 from the recovery value, and then both the mean value and the standard deviation value on the relative bias can also be calculated. It is easy to demonstrate that if the standard deviation of the relative bias is calculated as population, which is the population standard deviation, the value of the mean square of relative bias, that is the square of the bias uncertainty component, is equal to the sum of the square of both the mean and the standard deviation of relative bias. Therefore, in the case of no recovery correction, the final formula for the relative standard uncertainty would be the one that appears at the end of this slide. The square of the relative standard uncertainty is equal to the sum of the squares of the mean of relative bias, the standard deviation of the population of relative bias, and the relative standard deviation of recovery values. When the analytical results are reported corrected with a recovery factor, that is, multiplied by 100 and divided by the mean recovery, the bias uncertainty component is actually the uncertainty of the mean recovery, which is equal to the relative standard deviation of recovery values divided by the root of the number of recovery tests. Therefore, in this case, the square of the relative standard uncertainty will be equal to the square of the relative standard deviation of recovery values plus this same value divided by the number of recovery tests. That is, when results are reported corrected with a recovery factor, the relative standard uncertainty will only depend on the relative standard deviation of recovery values and the number of recovery tests taken into account for this calculation. Here are the two final formulas to be used to calculate the relative standard uncertainty in both cases: no recovery correction and recovery correction. Both formulas may be simplified in certain cases. For example, when the results are they are reported corrected with a recovery factor, and the number of recovery tests used for their calculation is equal or greater than 9, the value of the relative standard uncertainty will be approximately equal to the value of the relative standard deviation of recovery values. If the analytical results are not corrected with a recovery factor, and it is assumed that the standard deviation of the population of the relative bias is similar to the relative standard deviation of recovery values, which is quite acceptable when the mean of relative bias is small, it would suffice to know the mean of relative bias and the relative standard deviation of recovery values to calculate the relative standard uncertainty. The formula would be very much simplified if we assumed that the mean of relative bias is 0, which may be appropriate when using analytical methodologies that include procedural calibration or the addition of isotopically labeled internal standards before extraction. In these cases, the relative standard uncertainty could be calculated by multiplying the relative standard deviation of recovery values by the root of 2, that is, by 1.41. Now to finish, let's look at the two examples included in Proposal 1 of Appendix C, in which the concepts and final formulas we have just seen are applied. The first example, which is example A of Table 1, corresponds to a pesticide X, for which the result of 9 recovery tests are available. These recovery tests were carried out over 3 months as quality control samples, which were spiked samples at a level of 50 ppb on 9 different matrices belonging to the same commodity group: apple, pear, lettuce, etc. The mean recovery was 95.6%, with a relative standard deviation of 11.4%. In other words, this is an example of a pesticide that has good intralaboratory reproducibility and small bias, with a mean value of the relative bias equal to -4.44%. To calculate the relative standard uncertainty when results are not corrected with the mean recovery factor, we need to know both the mean and the standard deviation of the population of the 9 relative bias values, and the standard deviation of the 9 recovery values, resulting in this case a relative standard uncertainty of 15.92%, that is, a relative expanded uncertainty of approximately 32%. If results were reported corrected with the mean recovery factor, that is, multiplied by 100 and divided by the mean recovery, the relative standard uncertainty would only depend on the relative standard deviation of recovery values and the number of recovery tests used for its calculation. The estimated value would be, in this case, 11.97%, being the relative expanded uncertainty approximately 24%. It is interesting to note that if we used the simplified formulas indicated above, the approximate values of the relative standard uncertainty would be, in both cases, very similar to those obtained with the non-simplified formulas. You can see those in green. Example B of Table 2 is similar to the one analyzed in Example A, but in this case, the mean and the relative standard deviation of recovery values of pesticide Y are 71.6% and 11.1% respectively. In other words, pesticide Y shows good intralaboratory reproducibility, like in the previous example, but presents a high bias, being the mean of relative bias minus 28.4%. In this case, the relative standard uncertainty would be 31.42% when results are reported uncorrected with the recovery factor, and 11.67% when they are reported after being multiplied by 100 and divided by the mean recovery value. Again, it is important to note that in both cases, the approximate relative standard uncertainty values obtained from the simplified formulas are very similar to those obtained by applying the formulas without simplifying. And again, you can see them in green. And finally, let's apply these formulas to the internal quality control data, the recovery tests, presented in the example of the Codex Guide 59/2006 and its amendment of 2011. In this example, the available recovery values for a specific pesticide are coming from 14 quality control recovery tests that were carried out in a period of 3 months using blank samples of different fruits and vegetables with high water content and being the spiking level 0.5 milligram per kilogram. This table shows the pesticide concentration determined in each recovery test and the corresponding recovery values. The mean recovery was found to be 86.14%, with a relative standard deviation of recovery values of 15.36%. As indicated in the table, only with the recovery data we can calculate the two components, the bias and the precision, of the relative standard uncertainty in the event that the results of the analysis of this pesticide were reported after correction with the mean recovery factor, that is, multiplied by 100 and divided by 86. In the event that results are reported uncorrected with the mean recovery factor, we must calculate the bias component of the relative standard uncertainty from the relative bias values obtained in each recovery test and their corresponding squares. It is important to note again that the value of the mean square of relative bias is equal to the sum of the squares of both the mean and the standard deviation of the population of relative bias. Therefore, whether or not the results are corrected with a recovery factor, the only data we need to know to calculate the relative standard uncertainty will be the recovery percentages obtained in the recovery tests and the corresponding percentages of the relative bias. In this example from the Codex Guide, the relative standard uncertainty would be 24.30% when the results are not corrected with the recovery factor, and 15.90% when the results are reported corrected with a mean recovery factor. Again, we can see that the use of the simplified formulas leads to obtaining very similar approximate values, 25% and 15.5% respectively. If we adopt these approximate values as the final estimates of the measurement uncertainty of our results, the relative expanded uncertainty values that we would use in the test reports would be 50% if the analytical results are not corrected with the mean recovery factor, and 31% if the results were reported after recovery correction. To conclude, let's take this example from the Codex Guide to assess the significance of reporting a result either corrected or non-corrected with the mean recovery factor. This slide represents graphically how this laboratory would report an analytical result of 0.34 milligrams per kilogram. If the result is reported uncorrected with the mean recovery factor, the estimated relative expanded uncertainty would be 50%, and the result would be reported as 0.34 plus minus 0.17 milligrams per kilogram. In the event that the result is reported only corrected with the mean recovery factor, that is, multiplied by 100 and divided by 86, the estimated relative standard uncertainty would be 31%, and the final result would be reported as 0.40 plus minus 0.12 milligrams per kilogram. Well, in this particular case, if the maximum residue level was 0.2 milligrams per kilogram, in accordance with the decision rule established in paragraph E15 of the AQC guidelines, the result reported without correcting with recovery factor, which would be 0.34 plus minus 0.17 milligrams per kilogram, would not be rejected for exceeding the legally established limit, while the result reported after applying the recovery factor, 0.40 plus minus 0.12 milligrams per kilogram, would be rejected. It could be non-compliant. This is the reason why it is very important that laboratories and those responsible for making decisions in relation to maximum residue limits have clear and harmonized guidelines on correcting analytical results with a recovery factor, on estimation of measurement uncertainty of the results, and it's important that they have decision rules to establish when a result reported with its uncertainty exceeds a maximum residue level with a certain degree of confidence. In the AQC guidelines, these three aspects are included in section E, reporting results, and their analysis will be the objective of the second part of this tutorial. And this is all. We hope that you found this video tutorial useful, and many thanks for your attention.